Hello and welcome. I'm Claudia Rizzini, the Executive Director of the Radcliffe Fellowship Program at Harvard University. It is my pleasure to introduce our speaker today, Jane P. Chang, our Edward, Francis, and Shirley B. Daniels Fellow. Catalysts speed up everything we do in our daily life. Whether we're talking about enzymes like lactase that help us digest milk in our coffee, or the small amount of metal inside our car's catalytic converter reducing air pollutants. Chemical catalysts are invaluable parts of food and medicine production and crucial for clean air and clean energy. For a chemical engineer like Jane, the big picture is clear. A sustainable future depends on sustainable catalysts. But there is a tiny problem with not so tiny effects. With use, catalysts can get poisoned and damaged, rendering them obsolete. The constant need for new metals to replace these poison catalysts drives mining supply, often in war-torn areas of the globe. Jane's recent research asks whether it may be possible to restore catalysts to their original functional state. She is investigating the possibility of depoisoning catalysts using processes she refined over her decades of work in the field of nanoelectronics. Atomic layer etching, or ALE, removes single layers of atoms from the surface of materials. ALE has the potential to restore catalysts to their original functional states, reducing the needs for new mined metals. During her year at Radcliffe, Jane has been experimenting with using ALE to depoison copper. Her primary workspace this year is in Professor Dan Nocera's chemistry lab. To support her work in carrying out the experiment and quantifying the effects, she also worked with Harvard Center for Nanoscale Systems, the Lucian Purcell Instrument Center, and the machine shops across Harvard. Jane's approach is a testament to the power of thinking big by working small. And now please join me in welcoming Jane P. Chang.
Welcome, everyone. Thank you for coming to today's talk. And good morning and good afternoon to those who are joining online from different time zones. I wanted to start today's talk by sharing with you the following. These last 3 seasons has been truly remarkable, thanks to the Radcliffe Institute, its amazing and dedicated staff, my inspiring and supportive fellows, my talented and creative research partners, Edward, Francis, and Shirley Daniels, my research group back at UCLA, and most importantly, Dan Nocera and his entire research group here. Today, I'm going to talk to you about depoisoning catalyst for sustainable chemical processing. Why should we care about sustainable chemical processing? Because everything around us has been chemically processed at least once. And those processes require energy input, often a significant amount. And we all know that we need to conserve energy. Catalyst is a substance that can speed up these chemical reactions or lower the temperature needed to start the reaction without itself being consumed in the process. So this makes catalyst a truly wonderful material because it helps us reduce the energy requirement for chemical processing. And it technically can be used sustainably forever because it is never consumed. Today, I'm going to give you 3 examples as to why catalysts are important to each and every one of us. So we should all care about catalyst. Then I'm going to talk about 2 challenges associated with the usage of catalyst. One of them being poisoning, when something happened to the surface of the catalyst and it stopped working. This will then lead to my Radcliffe project, the solution to the problem to depoison the catalyst for their sustainable usage. So let us start. Why are catalysts important to all of us? Because catalysts address our basic needs, not wants, needs. We need to eat, we need to breathe, and we need energy to power everything around us. And catalysts support all of that. Let me first start with food. Catalyst is important in agriculture. When I was young, I thought ancient civilizations are called river valley civilizations because the rivers brought the water for agriculture. Indeed, water is important to help the crops grow. But later I learned water isn't enough to support the crop growth at the rate that is needed to feed a growing population. Those famous rivers, Nile, Tigris, Euphrates, Indus, Yellow rivers, all brought with them rich soil that make the land fertile. The soil contained one critical nutrient for the crops to thrive, nitrogen. Why nitrogen? Because nitrogen is at the heart of chlorophyll, which is responsible for photosynthesis. So crops can use the sunlight to produce food for themselves, not for us. Today, I won't have time to discuss the full nitrogen cycle in detail, but that process starts with the nitrogen gas in the atmosphere. The nitrogen molecule, N2, has a strong triple bond, which will make it highly stable and difficult to break apart. So as a result of that, the natural process of producing usable nitrogen for plants is a series of very slow chemical reactions. How do we speed up chemical reactions? We use catalysts. So scientists figure out how to break that strong triple bond with catalysts to make nitrogen-rich fertilizers. This is the history of world population mapping out over the last 1,000 years. The red circles here indicates when catalyst was first used at industrial scale to support the agricultural need. Interesting. We have learned from Judith Locke's talk that correlations are not causalities. So indeed, there are many reasons why the world population is growing the way it is. And they are indeed environmental issues associated with the production and usage of the fertilizers. However, in front of the world growing population, north of 8 billion, we must recognize that the catalysts help feed the world. Next, we're going to talk about the air that we need to breathe. The concern of air quality started with the Industrial Revolution, which brought us steam engines, cars, airplanes, automated factory, and mass manufacturing, all powered by fossil fuels. We learned from Jenny Stevens' brilliant talk, this is the start of one of the poly crises she mentioned. This was the skyline of Los Angeles in 1948. The situation was dire. People were having real health problems. Most of us are lucky that we only saw this in photographs. The Clean Air Act was enacted in 1955, which sets the health-based standards for ambient air quality. Among various mandates, now if you own a car, you know you have to take it annually for a smog check. What does it test? It checks if your catalytic converter in your car works properly to reduce the emission of pollutants such as nitrogen oxide, which can cause the smog formation. This is the skyline of Los Angeles, taken recently, thanks in part to the Clean Air Act and the catalysts. But some of you looking here, you will notice when the photograph was taken. It's in 2020, when the stay-at-home mandate was in effect. In fact, Los Angeles is one of those cities that saw its clearest sky during that time. So yes, catalyst in the converter was helping us with the air quality, but burning fossil fuels is still having an effect on the air that we breathe. Finally, I will talk about the energy that we need. Not just any energy. Today, we desperately need clean energy. This is a picture of the Charles River, taken just steps from here. If we can take the water from here, H2O, split it, we can produce hydrogen, H2, and oxygen, O2. Hydrogen is green energy, and oxygen we can breathe in. This sounds wonderful, right? Some of you might have just walked past the Charles River to come to today's talk. You know the Charles River does not spontaneously give us clean hydrogen. In Leah Stokes' talk, she mentioned several policy-based options that can help with greenhouse gas reduction. Two of them are 100% clean electricity standards and hydrogen production by electrolysis. She's basically talking about this reaction, my friend, if we put the catalyst and clean electricity to it. To address the energy problem, though, we cannot claim that we have solved the problem without addressing the elephant in the room, carbon dioxide, CO2. Chika Okafor used a very nice animation to show us the severity of the CO2 problem. And this year, we learned that the CO2 problem is not only affecting us, it's hurting the coral, the purple frog, and the humpback whales. What can we do to the CO2 problem? It turns out, in the presence of a hydrogen source, we can turn CO2 into useful and clean fuels. Again, this sounds wonderful. If this is a test problem, by now you know the answer to the fill-in problem. This reaction does not occur until we use a catalyst and clean electricity. Let me circle back to Leah Stokes' talk one last time. Of all the policy options for greenhouse gas reduction, the one that will make the most difference by 2050 is the industrial switching to clean fuels. If we want the industry to switch to clean fuels, we have to produce more clean fuels, and we have to make them economically. And this is where the catalyst can help. Okay, so by now, I have shown you that the catalysts are important because it addresses three basic needs of us: food, energy, water, food, air, and energy. Now let me show you some real examples so I can discuss the problem associated with using the catalyst. If you walk with me back to the chemistry department after this talk, you're going to see this periodic table at the entrance of the building. This is a very cool display. I encourage you to see it. It has the real material of each element inside. Let me show you some of my favorite elements. It went a little bit too fast, probably because I was not at the computer. Let me show you some of my favorite elements. These are 8 elements that are all metals that we are familiar with. As a start, we have iron that we use in stainless steel for cookware and construction. We have nickel and cobalt. We have nickel and copper, which are coin metals that we use in currency. We have platinum and gold that are precious metals that we see in jewelry. It turns out that these metals are also wonderful catalysts for various reactions. Iron can catalyze the production of fertilizer. Cobalt and platinum catalyze the electrolysis of water to produce hydrogen. Platinum and platinum are used in cars' catalytic converter. Silver and gold are used for organic synthesis. Nickel and copper can help convert CO2 into useful fuels. They all look so different, and they work best for different reactions. So what do they have in common? that we care about that affects their usage. Because you have touched and used these metals, you know they cannot be grown. They have to be mined. So the first issue that I'm going to discuss in terms of the challenge of using these metal catalysts is related to mining. One of the first books documenting mining is this one, Theoria Metallica. I hope I pronounced it correctly, published in 1556. While I could not read the original text in Latin, the book has many descriptive illustrations that are self-explanatory. In these black and white sketches, you see machineries, you see deep access tunnels, and you see people working above and underground to mine the minerals. Because of how inaccessible these metals are, mining is hard and dangerous. Now, fast forward in time by almost 500 years. This is a photograph of the Democratic Republic of Congo, taken from a New York Times article published several years ago. The photographs look quite different from the illustrations that I've just shown, but they feel so familiar. Machines, tunnels, people. Mining is dangerous. In fact, DRC is one of the world's richest countries in terms of mineral deposits. My research partners researched the history of mining in DRC and put together a timeline. According to the International Trade Association, the three largest exports of DRC are refined copper, cobalt, unrefined copper. In fact, DRC is the third largest producer of copper in the world and the largest producer of cobalt in the world. Yet, the country suffered from challenges associated with mining, dating back more than a century ago, starting from the colonization by Belgium. It is not just the danger associated with mining due to the natural environment. It is conflict mining. Conflict mining refers to the mining of minerals from parts of the world where armed conflicts directly interacts with and affects the mining industry. That conflict is intertwined with the DRC's long history of mining, contributing to ongoing violence, severe human rights abuses, and ethnic tensions. Last year, Matthew Eikens wrote the following in New York Times. The miners' exploitation is a symptom, not a cause, of their powerlessness, one element of a worldwide system of extreme inequality from which others benefit. Others, we, benefit. These powerful words made us want to do something. What can we do? If demand fuels supply, what can we do to manage the demand? In terms of the usage of metal catalyst, where is the demand from if the catalyst can be repeatedly used and was never consumed? It turns out that there are mechanisms by which the catalyst can become deactivated, and one of them is poisoning. To discuss catalyst poisoning, I need a model chemical reaction, and this reaction I'm going to use throughout my talk. The reaction I choose is converting CO2 into useful fuels. Then I take a metal catalyst, I zoom into the surface until I can see individual atoms. In an overly simplified view, this is what happens when we feed CO2 to the catalyst surface in the presence of a hydrogen source. Chemical bonds are broken and reformed, and we produce various useful fuels in gaseous or liquid forms. If the catalyst surface stays active this way, we can repeatedly use it. But you know, in reality, when we do this, things get a lot more complicated. As a starter, the carbon dioxide that we need to work with is not clean. They come from flue gas, emanating from giant plants burning fossil fuels. Even with the health-based emission standards, there are still traces of impurities, such as sulfur dioxide, that can act as a poison to deactivate the catalyst. Because this sulfur compound can bind strongly to the catalyst surface, it will make the catalyst stop working. If some part of the surface is covered, less fuel will be produced. If all of the surfaces are covered, no fuel will be produced. When your reaction don't work, you take out the poison catalyst. And then you ask yourself, what do I do? Do I throw it away and get new ones? Or do I try to regenerate it, remove the poison so that it can work again? The decision is not a scientific one. It's an economic one. If it's cheaper to throw it away and get new ones, you would do that. But that increases the demand, which fuels the supply, and we have just seen how problematic the supply could be. So, recognizing that poisoning is a surface phenomenon, can we do something about that process? Can we remove these poisons one layer at a time, restore some catalytic activity? Can we do a little bit more to remove the poison completely so we restore the catalytic activity to its original state? This brings me to my Radcliffe project, depoisoning the catalyst. To discuss depoisoning of the catalyst, in addition to the model chemical reaction that I have already selected, I now needed to choose a model catalyst. And I choose copper. And why copper? Well, copper is one of the metals that we as humans know for the longest time. The Copper Development Association called it the metal of civilization. Its usage dates back to the Bronze Age, and we are very familiar with copper. I chose copper for 3 reasons. One, copper is one of the least expensive catalysts among all the metals that I talk about today. 2, there are existing literature that indicates that copper is a good catalyst for converting CO2 into usable fuels. The third one is probably the most important one. My research group actually have some experience working with copper, even though it's in a completely different context. There we developed a process that I thought maybe this could be used to help depoison catalyst. So let me explain. Over the last 20 years or so, my research group has been working on chemical processes of materials that supported the microelectronics and nanoelectronics industry. Here on the screen and on the table, I show you a processed 8-inch silicon wafer. Each of the repeating patterns here is a die that can be cut out and packaged into a microprocessor that becomes the brain of your computer and smartphones. Inside of each of these microprocessors, there are many transistors. So I want you to think about transistors as a light switch, turning on and off electricity. They're not really light switches, but the analogy is a good one. As far as your computer is concerned, that on and off state corresponded to the 0 and 1 binary code that it needs for doing the calculation. So by putting more and more of these transistors together, we get greater computation power. Today we have supercomputers, artificial intelligence that can handle huge amount of data. Some of you online is probably streaming this talk on your cell phone because of the computational power that we have in our hand. Exactly how many transistors are there in these microprocessors? If you bought a high-end computer this year, you have about 100 billion of transistors working for you, personally working for you. That number is projected to go beyond 1 trillion in less than a decade. How do you fit that many transistors onto a space that is no larger than the size of your thumb? You have to make them very small. How small? Let's take a look. If we zoom into a single microprocessor and look in to the solid, before we find the transistor, we found a lot of copper. The copper that I'm showing you here forms a very intricate network. The reason for that is because copper has very good electrical conductivity, so we use this to form the electrical circuit for our transistors. This allows the individual transistors to communicate with one another and to cooperate together to do all of your computational needs. The largest copper size here are about micrometers. As a point of reference, the average thickness of your hair is 20 micrometers. The smallest copper wires that I'm showing here are on the order of nanometers. Nanometers are 1,000th of a micrometer, so they are very small. How do we make these structures? When we make things by our bare hand, what we make is comparable to the size of our hands. 1 nanometer is about 3 to 5 atoms in size. So if I wanted to shape something like this, the tool that I need would need to be around the size of atoms and molecules. That is exactly what we do in developing atomic layer processes. We use atoms and molecules to our advantage to do surface chemistry. Let me try to explain this. We start these processes typically with an absorption cycle. I use these green spheres to illustrate the gas molecules coming down onto the surface, which is shown in gray. The chemistry between these two types of molecules are specific. So once you form a monolayer coverage on the surface, the reaction will not continue. They will not accumulate on top. So you have one atomic layer of material to work with. Then we switch the process to an activation cycle. This activation cycle, I bring in a second chemical species, or I use an energy transfer process, or both. Depends on what I do here. Two things can happen. One, the absorbed layer on the surface can be converted into a solid and stay on the surface. This is an addition of a layer to the surface, and we call this atomic layer deposition. Or the layer that you introduce to the surface binds so strongly to the first layer of the material, weakens its interaction with the underlying layer, and you pour it off into the gas phase. You remove one layer of material. This is a subtraction process, and we call this atomic layer etching. By now, you probably have guessed that this activation step, where we use a chemical or energy or both, is the most important one because it decides the outcome of the process. So let me try to focus on this one and explain how this works. We have to create the fourth state of matter, a plasma. We are familiar with the 3 states of matter, solid, liquid, gas. If I take an ice cube, I heat it up, I get water. If I heat it up some more, I get steam. So that is phase transition from solid to liquid to gas. Phase transition takes place when you increase the temperature. If I keep going in temperature until I reach above 10,000 degrees Kelvin, I start to pull some of the electrons from the molecules. And then I accelerate these electrons. I allow them to ionize and dissociate the molecule. I create a very complicated, partially ionized gas mixture that is called a plasma. A plasma is a wonderful gas phase chemistry tool that we can use to shape nanoscale features. Because it has positively charged ions and reactive radicals. These ions being charged, I can use an electric field to direct where I wanted it to go. And usually I want it to go perpendicular to the surface. Through the momentum transfer, I can dictate the direction of the chemical reaction. Giving chemical reaction a direction is critically important to pack a trillion transistor into your microprocessor. The radicals that we have in the gas phase are so reactive that they help lower the temperature on the surface that is needed for this reaction to take place. In many ways, it's similar to what catalyst does, lower the temperature that is needed for chemical reaction to occur. So by combining the unique aspects of the ions and radicals, and also their synergism, we can create these high aspect ratio features. We can code these high aspect ratio features with conformal thin films. By iterating this process, we can build complex structures involving multiple materials that is needed to support our computing needs. Before I go to the next slide, which is the heart of the slide, allow me to go off the tangent for 30 seconds here. Because the plasma's unique property to break down gas molecules so effectively, in recent years, it has been used to help with environmental protection. Plasma can be used for the abatement of volatile organic compounds, remove sulfur dioxide and nitrogen oxide from the flue gas. It can be used for wastewater treatment. So even though today I don't have time to discuss these aspects, the plasma is important for environmental protection. Coming back to the point of the talk, atomic layer etching is a wonderful process, and my group has demonstrated that we can use this process to remove atomic layers of copper. We do so by using an oxygen plasma, and we use this particular process to modulate and control the directionality of the formation of copper oxide. Then we use an organic acid vapor to react with the surface and selectively remove the copper oxide from the surface, forming these complex and volatile compounds. Etching copper is not hard. We know how to do that centuries ago. But etching copper in the gas phase is very hard. Many people have said this can never happen. Never happen. Well, we made it happen. Because we made it happen, a question that we wanted to ask at the time when I was writing the Radcliffe proposal is whether or not this process can be leveraged so that we can remove just the surface layer of the poison from a catalyst surface, like copper, so they can be sustainably used. Here I wanted to pause and thank the Radcliffe Institute for giving this inquiry an opportunity, even when they knew I've never worked on catalysts before. I wanted to thank Daniel Seyer for his incredible generosity for opening his lab for this project. And I wanted to thank his group for welcoming me and teaching me how to do electrochemical experiments. Over the last 6 months, we have been working on electrochemical reduction of carbon dioxide with copper. I work closely with my 3 Radcliffe research partners, Kate Guerin, Abibesi Nyumbani, and Sarah Shirley. In this electrochemical cell that you have here, we use copper as the catalyst. We pass a current through it. We introduce CO2 into the system, and then we monitor the formation of the reaction product. Some of them are in liquid form, and some of them are in gaseous form. We went through multiple iterations of this experimental setup, and thanks to the patience of all the people who helped me in the process, we got a system that works reproducibly, and samples has been flying across the country because the atomic layer processes still have to be done by my research group at UCLA. We got a lot of data. Period. We can pack up and go home. We have a lot of data that I'm not going to show you today. I will show you the most important one. Because we're looking at the poisoning effect, I have to quantify the sulfur. I needed to know how much sulfur are there and in what chemical environment it is in. So I use a technique called X-ray photoelectron spectroscopy. As shown in here, I can measure the concentration and the chemical bonding state of each of the elements on the surface, including sulfur. Once I have this information, then we monitor this concentration as we do the electrochemical experiment to recover the activity of the copper to see how effective we are. I also have to quantify the reaction products. So I use a gas chromatography system to measure the gaseous products, such as methane. I use the nuclear magnetic resonance techniques to measure the liquid product, such as ethanol and methanol. And here comes the proof of concept data. It's a blank figure, because I want to explain to you the axes first. The first y-axis shown on the left is in purple. That shows the concentration of sulfur. The second y-axis on the right is shown in green. That is the efficiency of the product that we generate. And I have 3 sets of data. Each of them carry the 2 sets of information, sulfur concentration and efficiency of product generation. I have on the bottom clean copper, poisoned copper, and regenerated copper after we treat it with the atomic layer etch process. Okay, let's look at the sulfur concentration first. The clean copper surface has no sulfur, so I force a line at 0 there, very faint purple line here. We use a model compound to introduce, actually we use 4 different model compounds, I'm showing you one here, to introduce sulfur to the surface, and we can quantify its concentration and the chemical environment. After we treat the surface with atomic layer processes, we reduce the sulfur concentration down to the detection limit of our instrument. The reason why I mentioned the detection limit is important, because I'm going to come back to that point in just a second. Okay, so we know what happened to the sulfur in our processes. Let's now look at how that affects the products that we produce. How much we produce from a clean copper surface is our baseline. We have to benchmark against this to know what effect we have when we poison and when we clean the copper. Okay, so that's our starting point. After we poison the surface, that green bar dropped to essentially 0, very, very low. Did not go to 0 because we used a model compound. We didn't use the flue gas. But the effect is clear. The sulfur poisoned the catalyst, and we cannot use it effectively to produce the products. Now, we treated the surface with our atomic layer etch processes. I'm going to show you 3 sets of data because they are interesting in their own ways. The reason why they are different is because we tweaked the process conditions that we used. But here is the data as a group. I want you to first look at the data and agree that compared to the poisoned surface, we recovered the catalytic activity. Maybe we didn't always recover it fully, but we recovered the catalytic activity. So that is good. Why are they not the same? 2 of them appears to be not as good as the clean surface that we started with, and we ask ourselves why. So this is where that detection limit comes in. We remove the sulfur down to the detection limit, but we need a better, more sensitive technique to tell us if we truly remove all of the sulfur. We suspect there's still some sulfur there, probably on the order of a fraction of the monolayer, but we cannot detect it with our technique. But the effect was good. The most interesting one is we have one set of data where we have significant improvement compared to our clean surface. Why? If we remove the sulfur completely, shouldn't we just restore the property? Why are we changing it? Why are we making it better? It turns out that in that particular condition, we use a slightly more aggressive plasma. And that particular plasma, when we look at the surface of the copper using a scanning electron microscope and atomic force microscope, we see that the microstructure and the morphology of the copper has changed. In catalytic literature, that is usually a cause for increased efficiency in the product formation. So clearly, there's room for improvement so that we can fully understand these processes, but the proof of concept is done. We have shown that the atomic layer etching process can depoison the catalyst and restore the activity. Where this work can be expanded in the future is to target metal catalysts that are scarce in reserve and are most impacted by conflict mining. I wanted to use this slide that I borrowed from Daniel Serra to conclude today's talk. The global energy usage is going to continue to increase quite substantially, and you have already heard it from Leah's talk. This number will increase despite of what we do on energy conservation. We can hold this energy intensity constant or even lower. That number will still go up because the world population is increasing and the world economy is growing as defined by GDP per capita. So as long as we use carbon-based fuel, per unit energy we use, we are going to produce CO2. So the CO2 production globally will go up. This is a challenge, but potentially an opportunity. If we must continue to use carbon-based fuel, at least for some time, we must focus on CO2 capture and conversion of CO2 into useful fuel. This is an area where catalysts can help. We can potentially help achieve a carbon-neutral distributed energy system that is low in capital cost. But we also must look beyond carbon. We need to look at non-carbon-based energy. We already discussed a little bit about hydrogen today. Nitrogen-based fuel is emerging as an alternative, promising alternative to hydrocarbons. And I also wanted to say that the intersection of using plasma and catalyst is a relatively new field and bring us the promise of combining the synergism of these two processes to help with fuel production and environmental protection. Clearly, to solve the global energy problem, we must work together. We all know the importance of interdisciplinary research because the whole can be greater than the sum of parts. I have participated in many interdisciplinary research programs in the past. So far, I found this year's immersive program through the Radcliffe Institute is the most effective in promoting that effort. Thanks to all of you. So with that, it brings me to the most important slide of the talk. All the people who supported me in this journey, I have negative 20 seconds. So if I try to go through the list, it's going to take up all the Q&A time. So I'm not going to do that, but I wanted you to know that I'm grateful to you. Thank you very much.
Thank you so much, Jane. What an enlightening and exciting presentation. And it's been such a pleasure being a fellow with you here. And I'm really excited to get to ask you some questions. We have a number of questions. One of the questions people are really interested in understanding is how does the kind of energy benefit of this compare to the energy inputs in terms of making plasma? It seems like making plasma for this purpose would be really energy intensive. Can you give us a sense of how much energy needs to go into depoisoning these catalysts?
Yes, thank you very much for that question. One of the reasons that plasma was not used for this purpose, especially decades ago, is because the energy efficiency is not there. But more importantly, the electricity that we use wasn't clean. And I mentioned to you that recent years, this has been used to address some of the environmental issues because it is becoming energy efficient. Not just because the instrument design and everything uses energy more efficiently, but because the electricity that we use are cleaner. So when we can reach the goal of 100% clean electricity, that's when this will be very effective.
Another question is this more aggressive form of depoisoning. Can you say a little bit more about how the surface morphology changes?
Yes, so we see the roughness increase. So at the atomic scale, that means you see these hills and valleys. So if nothing else, that increases your surface area, right? And your efficient measures against the surface area when you have a planar surface versus when you have a rough surface, that changes. For people who study catalysts of copper and other metals, the crystal structure of these metals dictates that when you have different cuts, when your atomic arrangement on the different surfaces are different, their catalytic activities are also different. What we were able to produce using the plasma is a polycrystalline roughened surface. So it takes advantage of some of those atomic arrangements that help promote the catalytic reaction.
That's such an interesting finding, and I wonder if beyond being able to depoison the catalyst to improve the output at the end, that could actually inform the creation of the catalyst in the first place.
Yes, so there are actually literatures existing where people use non-reactive plasmas, right? They use a noble gas to generate a plasma for the sole purpose of creating roughness, creating microstructures on surfaces. And they can see that it changes the catalytic performance, not just in terms of efficiency, but also in terms of selectivity. One thing that I didn't address today is about the production of fuels. When we can make many fuels versus when we can make one fuel, which one is better? One is better because when I make many, I have to separate them. The separation process is an energy-intensive process. So making a lot of fuels of different types is great, but the catalytic field right now is actually focusing on tailoring the selectivity so that we can produce one well, and we don't have to go through a separation process.
So that's another question that's come up here several times among the listeners. They're wondering, what is the diversity of products being produced, and are there specifically waste products or undesired products that come out of this process as well?
As a chemical engineer, I would say no chemical is undesirable. They're all useful in some ways. So yes, we produce a lot of different chemicals, but I think for this particular question, we can find ways to use any of these chemicals, but exactly how we can use them. We cannot go here and say, ethanol, line up, and then go out this door, and then, yeah, okay. So we have to do additional chemical processes to them, and that is an energy input as well. So yes, the field is evolving and is converging, and right now the challenge we have is how do we target what we want to see from it.
And today you focus mainly on copper as your example and as your model for developing this. Would the process be very different for other types of metals, or what sorts of challenges might you face if you were to try this with cobalt or iron or a different metal?
Great question, thank you. So the processes that we're developing is really targeting what is absorbed on the metal surface. So when you change from copper to gold, for example, gold is known to bind very strongly to sulfur. So that will require a little bit more energy for you to break it apart, right? But the concept doesn't change. We might need to tweak with the energetics of the species that we have. We might even need to change the chemical slightly, but the concept will remain the same.
And I know one of the big challenges kind of transitioning from the basic chemistry to the engineering challenge of production is scaling up. So right now you've been doing this at a relatively small scale. Could you give us a sense of what the scale is at which you're depoisoning, like how large of a piece of copper is being depoisoned, and what the process might be or how that process might change as you scale up to industrial levels?
Okay, so my group work on atomic layer etch and atomic layer deposition processes. In my lab, everything that we treat is about this large in size. Centimeter square is our standard. Atomic layer deposition process was invented 50 years ago. This year, the community is going to celebrate its 50th anniversary in Finland. The first 30 years, no one wanted to use the process. No one. It was too slow, not economical. It was scientifically interesting, beautiful work, not a single application. Not until the microelectronics industry hit a bottleneck in scaling its transistors. Couldn't do it with the existing material. We have to do it with atomic layer deposition process. It took 10 years, but in 10 years, that process went from not economical, not possible, to mainstream in today's IC manufacturing. The equipment vendors that makes the atomic layer deposition tools are starting to make atomic layer etch tools. Right now, the application in terms of these two areas, atomic layer etching is still fairly new. I will never make industrial scale tools in my lab, but the infrastructure is there and the proof of concept at the industrial scale has already started. That is in the microelectronics industry. It has not been used in the catalysis field, where the atomic layer deposition process for microelectronics first emerged or intersect with the treatment of nanoparticles is to take a chemical engineering conventional unit operation, a fluidized bed, and make that particular process possible. So there is examples that these processes can be made at scale for more traditional chemical processes. Has not been demonstrated for ALE, but if there is demonstrated performance, the work is not too far away.
One of the things you touched on is the various metals that are used as catalysts. Some are much more abundant than others. Some are quite rare. Some involve much more intensive and polluting mining than others do. So taking those sorts of factors into account, which metals do you think should be high priority for developing these depoisoning strategies?
It really needs to be the metal that are the most scarce and are the most impacted by conflict mining. The commodity metals has been around for a long time. Not saying that the practice is ethical, responsible throughout the world, but it's less of a concern. So the focus really should be in the area where these issues on the supply chain side is the most problematic.
And could you say a little bit more of what proportion of these metals that are currently in use do come from conflict areas as opposed to other forms of mining that are more regulated or more controlled?
That is a question outside of my comfort zone, but I will try to answer. The International Organization for Economic Cooperation and Development only recognizes 4 metals as being the conflict metal. And none of them is the 3 most major export from DRC. And the Organization for Economical Cooperation and Development also have a due diligence guidance that they put together to help industry with responsible sourcing of minerals from conflict-affected or high-risk areas. But it is a guideline. Don't know if there's an international organization reinforcing that. So in terms of recognized conflict metal, tin, tantalum, tungsten, gold are the only 4. But the images that we seen today, mining in DRC, copper and cobalt are the largest metals. They are not on the list, does not mean that the issue isn't there.
One question that's come up is, you've shown, I think, really effectively how you can depoison the copper in this example once. Have you tried doing it multiple times? Are you able to recover that same efficiency after multiple depoisoning attempts?
I'm staying for the summer. That's what I'm going to do. As a person entering into this field, the minute I walk into Daniel Sayer's lab, I thought, based on everything that I read, right, I should be able to learn this. In a few weeks, and I can start doing this. No, it's very hard. It's harder than some of my ultra-high vacuum processes that I developed. There are a lot of the details that goes into how to make an electrochemical cell that is reproducible. The amount of care that they put in to make sure that the process is properly functioning is tremendous. So I'm glad that we were able to do what we did in 6 months, and we'll see what we can do in the next 2 months.
Well, personally, as someone who runs a lab, I'm so impressed with what you've managed to accomplish in 6 months. And so I wanted
to have a lot of help.
Yeah, so I wanted to ask a little bit about your collaboration with Dan Nocera and ask about kind of how that came about, and could you give us a little bit of insights about working together?
Yes. So I can spend an hour talking about Dan Nocera, but I'm not going to do that. He is, of course, the world-leading figure on bionic leaf and proton-coupled electron transfer processes. I do not know him when I was writing my Radcliffe project proposal. But I contacted him. And he said, OK, let's do a short Zoom meeting. And we talked for less than 15 minutes. He said, that sounds interesting. Let's do it. And so by the time I started this, I joined his group. It is not just his accomplishment in the field that drew me to his group. It is also his vision. He's a great chemist, but he wanted his chemistry work to have an impact. And since I joined his group, I found that he has instilled that in his group. Everyone is doing the same, great science with an impact. And I think that is what we need for the future.
One of the things you also highlighted was the incorporation of students in your work. Could you say a little bit about what that was like? Did they have a background in this area? How did you get them started?
Okay, I did not have a background in this area, so working with my RRP students, it feels like going back to graduate school. We have to learn everything new. We are making mistakes at the same together. We are finding how to do things properly together, and that has been inspiring. They are very creative. They ask very good questions, even though they are new to the field. And I learned a great deal from them, and I really appreciate the Radcliffe Institute for offering that research partnership program.
And so there's a lot of interest and enthusiasm in these processes that you're developing. So I'm going to close with our final question now. And this one is pure speculation, because I know you probably can't answer it. But when do you think this might be available for commercial use? When do you think the reality might be here where we could depoison catalysts at scale to help reduce our net carbon usage?
I cannot answer that question, but I can answer that question. It's really a matter of funding and effort. If the research funding support is there, it will happen. With concerted effort from many brilliant young scientists, this will happen. But for environmental-related problems, especially, for example, in the microelectronics industry, every time the environmental issue is a problem, we work to solve them. When we hit the goal, everything drops off. 20 years later, we repeat that process again. And during that time, a lot of the knowledge have been lost, because not everything that is done in industry is published. So you lose a lot of know-how. So if we can sustain that process, this is really just a matter of will to do it with available resources.
All right, on that note, we're now at time, so I want to say thank you so much, Jane, for this amazing and really educating presentation. I've learned so much. We want to thank the audience for all of their terrific questions, and we hope you'll be able to join us for other Radcliffe virtual programs. You can find out more about future programs and watch videos of past events at radcliffe.harvard.edu. And thank you all, everyone, again for joining us, and I hope you have a wonderful day.